Hello everybody, how's it going? Welcome back to Alex Does Lead Code, where I work on programming problems with you on stream. I should add like some kind of music here. Like intro music, I see other YouTubers do it. Okay, alright, so today we're going to continue the problem we were working on from the last time. Last time we were working on a problem called substring with concatenation of all words. And just as a quick recap, we managed to get our solution most of the way there. Excuse me. So you can see that our solution got us most of the way there. It works on the basic test cases over here, 1, 2, and 3. Actually, let me zoom in a little bit. This is too big. Yeah. Okay, cool. This is the right size. It works on 1, 2, and 3. But when we run it, when we try to submit it, there are certain test cases that it fails on. And the last time we talked about how these failures are probably because there are multiple duplicate words or words overlap or contain each other. So you can see our answer currently works for 160 out of 179 test cases. Which, you know, it's good. It's pretty good. But not perfect. Unfortunately, in programming, pretty good is never enough. We need things to be perfect. Alright, let's take a look at what's happening. Good, best, good. Okay, so here's the case where it fails, right? We talked about this. When there are multiple occurrences of the same word. And I'm pretty sure... it doesn't allow me to look at it. Just look at one at a time. Oh, upgrade to premium to use debugger. Interesting. Let's see if I can do that next time. Okay. I like Python Tutor though. Python Tutor has a graphical debugger, which I don't think I've seen another IDE have. But that's a discussion for a different time. Okay, all right. Let's see what's happening here. Let's do a quick recap of what our algorithm is. Okay, what was our strategy, right? So actually, let's start by recapping the problem. So what is the problem we're trying to solve today? We are given a string S and an array of strings words. All the strings of words are of the same length. A concatenated string in S is a substring that contains all the strings of any permutation of words concatenated. So for instance, if the words A, B, C, D, E, F, then A, B, C, D, E, F, A, B, E, F, C, D, you know, just jumble them around. Those are all concatenated substrings. But A, C, D, B, E, F is not. You can jumble each of these individual strings around, but you cannot mix and match their letters. So there is no AC anywhere here. So that's not going to work. That's not going to work. Okay. So the last time we left off, we had an algorithm that looks something like this. First, we create this thing called an occurrence dictionary. An occurrence dictionary looks like this. You have some kind of lookup. You have a mapping from the index to the word that actually appears. Okay, you have an index from the word to the word that actually appears. So for instance, in this example, foo and bar are words inside this list of words. And foo bar man, bar foo, the foo bar man, is the string S that we are searching or we're looking through. So foo occurs in 3 and 9. So foo occurs in 3 over here and 9 over here. Okay, so 3 is foo, 9 is foo. And then bar occurs in 0 right here at the beginning, and 12 over here. Okay, so we're full bar, bar, bar. We're full and bar. Now, the last time I mentioned that there are two cases where this algorithm fails. Sorry, I need to continue. I'm not in my A game today. Let's restart the explanation. So you have an occurrence dictionary that looks something like this. Okay? Once we have this occurrence dictionary, what we did is we go to each of these in turn. We go to 0 first, and we see, okay, well, we want these words to be repeated, right? Want these words to be repeated. We want to check if there is they call it a permutation. What do they call it? Concatenated substring. We want to check if there's a concatenated substring at bar. So we go to 0, we check there's a bar. We need full and bar. Well, let's check 3, is there a full? And yes, there's a full, so 0 is an answer. And that's why we do what we're doing here. With start and word inserted. Okay, so this is the lookup that we're talking about. Valid equals true. This valid tells us, is there a concatenated substring that starts at start? That's what it tells us. Okay. And then we look through this and try and figure out what's going on. Okay. So the problem we had, the last time we identified two problems with this algorithm. One, it doesn't work when there are multiple duplicated words. We already see this. When we run this, there's word, good, best, good. And the reason why has to do with the way we check validity over here. The way we check validity is we just go over the string. So for instance, we want to check validity where start equals 0. We'll check 0. We'll check 3. And we want to make sure each time we hit a unique different word. So you see perm.append words index. So if perm already contains that word at the index, then it'll fail. Which means this gets us to a tricky problem where good appears twice. So you know what? Actually, let's do the following thing. Let's put this in a Python tutor. Let's visualize this, and let's see for ourselves what the problem is. Let's see for ourselves what the problem is. I do want to note that the last time I said another problem when words overlap or contain each other. Okay, so for instance, foobar. This, however, is actually not a problem because we know that all the words are of the same length. So either they are duplicates or they're not. Otherwise, they can't actually contain each other. There's no way you can have an index that contains something like this. 9 foobar. You can't have this. This is the problem that I was thinking about. Okay, but apparently that's not a problem. Let's visualize this a little bit. So today our job is to fix the bug, and maybe if we have time, maybe we'll make this algorithm a little bit nicer. All right. Let's copy our input here. we should probably do this. Or we can probably do this. But I don't think I want to do that right now. So find all, instead of self.find all, it's just regular find all. Okay. Cool. So find substrings as words. As words. Alright. Let's visualize execution. Let's see what's up. Okay. So we're gonna skip these find all things. They're not super helpful. We're gonna skip creating the occurrence. Instead, what we're gonna do is we're gonna jump all the way to here. Okay, so we're here. So where the program is right now is that it's got words, results, blah blah blah. It has this lookup table. So lookup table says 0 is this is kind of hard to read. Okay, 0 is word, and then 4 is good, 8 is good, 12 is good, and then there's best, and there's word. Okay. And so what we're going to do is we're going to, for instance, start at 0. Okay, now start is at 0. So we're just as a refresher, what we're doing right now, what the program is doing right now is checking if there's a valid concatenated substring that starts from 0. So the answer is no, because at 0 you have word, good, 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 best, word. And here you have word, good, best, good. So it should be no. There isn't one that starts from 0. There is, however, one that starts from 8. Good, good, best, word. Good, good, best, word. So it should work when start equals to 8. It should not work when start equals to 0. So let's see what happens when start equals to 0. So what it does is that index is to 0. You know, index not equals lookup. It says words at index lookup index. It takes the first word. Word at IDX. Word at IDX is just word. And then it adds that to perm. So far, all good. So perm now contains word. Perm contains word. Now IDX is 4. Perm should contain good. It checks is good inside here. Now perm also contains word. So perm is word and good. Okay. Now IDX is 8. So IDX is 8 now. I'm trying to see what's the best resolution to make this. Okay, so IDX now is 8. And if I go next, words at IDX. Words at IDX should be it's this one right here. Good and good. So word at IDX 8. There's good. The reason why it's good and good. The reason why this is good and good is because one of the goods is 1, and one of this the other goods is this. So there are 2 goods in our word list. There are 2 goods in our word list. And that's where the problem comes in. So it then checks, does good appear in perm? And it does appear already in perm. So it says, well, you've already used the word good. You can't use it again. But hey, we have two goods. We should be able to use it twice. Yeah? We should be able to use it twice. So that's a problem. That's what's happening. So I think the way I want to solve this problem. So that's the bug. So the way I actually want to solve this problem, let me think about it a little bit. There's a few ways I have of solving this problem, but the first one that comes to mind is as follows. I am going to create a dictionary that tells me how many times a word appears in the word list. I want to create a dictionary that tells me how many times a word appears in the word list. So in this case, words will be the word good would be 2 because it appears twice in our word list. Right? It appears here and it appears here. And then that makes it easier for checking duplicates. Maybe not. Maybe I won't do that. Okay, I have a better idea. So let's change how perm works. So perm right now gives a Okay. So perm right now is an index. And I don't think I want that. Actually, I don't need occurrences, so let's take that out. That makes it, a little bit less painful when we're debugging and looking at things. So perm right now looks like this, right? Word good. And so that's the problem that we have with perm. So we have word good, and we want to know that the second we should be fine with putting the second good in. But right now we're not, because perm just says word good. Okay, so I have an idea. So instead of making perm a list of words, we're going to make perm a list of indexes. We're going to make perm a list of indexes. Okay? We're going to make perm a list of indexes. And the way it's going to work is that when we're going to make perm a list of indexes. And the way it's going to work is when we see a new word at index, we are going to look at words and then add its index to perm. And so when we see the same word appear twice, for instance, we see good appears twice, the first time you'll add 1 to perm, the second time you'll add 3 to perm. Okay, so let's walk through this a little bit. Example. So when start equals to 0, perm equals to word, right? So perm should be 1. When start equals to 0. Oh, no. IDX equals to 0. There's an inner loop, so IDX equals to 4, perm equals to 1, and when IDX is 4, we see this good here, so we say we look for good, and it says there's a good here. Well, 1 and 2 equals to 8, perm equals to 1, 2, and sorry, not 1. What am I thinking? And 3. So 0, 1, and 3. So this will give us the machinery to distinguish between the two goods. So we have 1 and we have 3. Yeah, so this will give us the machinery to distinguish between the two goods. I think it's okay. You know, I think it's a way of doing it. I don't know if it's necessarily the best one. So the other way I was thinking of looks something like this. So originally what happened was perm equals to word, and good. And then now perm is stuck because it sees the word good already. It sees that the word good appeared already. So it says, hey, guys, you've already used good. You can't use it again. When in actuality, we can use good twice. So there's another way of doing this, where we say times, where we have a dictionary that tells us how many times a word appears in the word list. And then when start equals 0, perm equals, so perm in this case will also have to be a dictionary. Good 1. Okay, and we get to index perm equals to 8. We have good 2. So this mechanism again allows us to tell that the word good is being used twice, and we're allowed to use word good twice. So we'll pick one of these strategies. Actually, let me see. This might be a little bit faster, this one. But this is easier to understand, so I'm going to go with this. You know, this is a learning channel, and it's often really difficult to understand what other people's code is doing. So we're going to try and make things as easy to understand as possible. So let's try with this one. Okay, example as blah, blah, blah. Okay, so we're going to make perm. Instead of making perm a list of words, we're going to make perm a list of indexes. And we're going to have some function to find next not in perm. Okay, I'm going to also make a few changes because apparently lookup does not need to be a list, a dictionary of lists. Instead, we can do this and turn lookup into a dictionary of words. Okay, so this is the part of the code we need to change. So we have word at index. So let's come back to here. This is what we're looking for. This is what we're gunning for. Let's paste it to the top. Make it easier to see. So this is what we're gunning for, right? When IDX is 0, perm should be equals, we should set perm to 0. We should look for word and index. Word of index is going to be word. And we should set perm at 0. Let's create a function. Find next not in perm, where we give it perm, we give it words. This is going to be tricky. So we're going to create a find next not in perm function. And so again, this is just good programming habit to put things into functions when logically they form a distinct unit. So find next not in perm, and the way I'm going to do this is basically it's very similar to this. It's the same as find all, really. It's the same as this find all. But with a few changes. If index in 0, okay, IDX smaller equals to -1, return -1. If we find it, we check, is this in perm? If the x in perm, not IDX in perm, return IDX. Oh yeah. Yeah. New copy of this word we haven't used. So perm is the list of words that have been used. So here's a new copy of the word we haven't used. Not used. Okay. And then otherwise, yeah, I think this should work. Find next not used. So previous index equals 0. Yeah, find next not used. If IDX not used, okay. So previous index while true, find the substring oh, so it should be words dot find. Oh, this is a bit different. Okay, let's find index, find value, Python. How do we do this again? It's just dot index. Okay, cool. So words dot index. Yep. So it uses same Okay, words dot index. Find next word previous IDX. Okay, so it uses the same. It's basically the same idea as find all. It's basically the same idea as find all, except that we are looking for word in a list rather than a substring in a string. So this part looks a bit different. But otherwise, find next not used should work. So it's words, word and index, and then perm. I should rename perm to used. So if I can't find next not used, that means valid equals false. Break. Else use dot append next. So it's a very similar idea. If I can't find a suitable word inside words to use for perm, i.e. it cannot be already used, then break. And I think this should work. Let's run it. Concat into tuple. Start plus length. Oh my god, what's happening? Start plus n times length. I think I did something weird. N. I think it's this N. Can only concatenate tuple to tuple, but start is a tuple. This is weird. Let's replace it and see what happens. In our visualization tool. Okay, we're gonna edit this code. We're gonna replace this for IDX part. We are also going to add our new function that we've written. This find next not used. Otherwise, it's not going to run. Okay, we're going to run it and see what happens. It should fail. Yep. Used is not defined. No, it doesn't fail in the same way. That's interesting. Oh, use is not defined. Let's see what happens. Word is not in list. Oh. Okay. This is kind of weird. Can only concatenate tuple, not integer. Oh, start is... So lookup is weird. Let's check lookup. I think lookup might be the problem. Lookup looks like this. Oh wait, I didn't change the lookup. So I think I did something wrong with the lookup here. I didn't copy lookup over. So this is what I had before. This is what I've changed it to. Find all words. Index in indexes. Lookup index equals to word. Let's visualize execution. So lookup is an empty dictionary. What the heck? Self is not defined. Oh, oops. Where do you see self? Wait, where's self? Let's run it again. Okay, lookup indices equals self dot find all. Okay. So this is something is wrong here. Let's try and see what's going on here. So word in words. So I'm doing something wrong with this lookup, right? So I'm doing something wrong with the lookup. Because how do I know this? Because something happened here that makes this not right. And I think it has something to do with start. Oh, start word in. Keys. It's keys. I see. So this is what I was doing wrong. I changed this. So start word in sorted lookup.items. I actually didn't want lookup.items. I don't need the second part. I just need all the starting indexes. I just need all these starting indexes. These things. I need these things. I don't need these things. So I need to say dot keys. Otherwise it will give me something weird. Okay, this should do something right. Find next not used. Self.find next not used. But 4 were given. Oh. Good not in list. Okay, so we now have the same problem. Okay, so instead of doing this, we should say if instead of try catch. Let's look up how index works. So index is a built-in function. Error value raises. This is a little bit annoying because I need a try catch. I was initially doing something that looks like this, word in words. But I can't do this. I can't do this because of the previous index, right? This will not give me the same answer as this because I'm missing the previous index. If not word in words, and there are multiple occurrences of word, then On the second one, it will not do the right thing. Okay, so try. How do you do try catch in try accept? Okay, so this is going to be a bit weird. So I don't have to check for this anymore. It never returns -1. It just throws an exception. Yeah, it just throws an exception. Oh, it should return, sorry, it should return -1, yeah. Okay, so we're back to this working well. Let's see if it works for the case that we had problems with just now. Let's just add this to a Python tutor. This is not looking up. Time limit exceeded. Okay. Oh, interesting. So this is a new problem that we have. This is a new problem that we do have. Because our strategy for finding the next word is very slow. It's too slow. Look at what's happening here. So I'm pretty sure that we have fixed the previous error we had, but this is a brand new error. And this, unfortunately, oh, you see, it's 174 out of 179. So we have 5 more test cases, and this is probably the big one. If we do sort of analysis on our strategy, if we do sort of like big O analysis on the way we strategize, lookup is going to be pretty huge. We're gonna go start in sorted. Okay, we're gonna start, and then yeah, this is not great. Maybe creating. Okay. Maybe creating this lookup was unnecessary. This is what I'm thinking now. I think creating the lookup was unnecessary. Like this lookup over here, it's unnecessary. Why do we create lookup? Why not just do a for loop where we go to each index one by one? When we are at an index, we just do this, right? Wonder if we can do that. We just do this. Okay, so we have the same general structure, but we don't use the occurrence dictionary this time, because I think the occurrence dictionary might be a trap. Because occurrence dictionary might be a trap. I think this is a pretty good example of actually, I'm happy that we got stuck here, because I feel like this is a very good example of starting with something that sort of works, right? We started with a algorithm that works pretty decently, 160 out of 179 cases, and then we fixed it, we made it better to look for the edge cases, and then now we realize that it's kind of slow, so now we iteratively make things a little bit better. That's a strategy that you have to employ a lot in real life, because in real life it's often not the case that you sit down, you think for a long time, and you plan out the best algorithm and the best strategy, and just go with that. right? In real life, very often what you do is you iterate a few times, you mess it up a couple times, and I'm sort of waffling here because I'm thinking about what is the best way to do this. I think maybe one thing I'll do is start by removing the occurrence dictionary. You know what? So the first thing I'm gonna do is to take this whole thing and say, well, we're gonna make a copy of it. We just call this define string 2. We're gonna hide it because we kind of don't need it anymore. Okay, when we just make a copy. Okay, so what are we gonna do? We're gonna not use occurrence dictionary. No more occurrence lookup dictionary. I think that would be faster. Okay, and then instead of start looking up keys, we have the same strategy, but this time for I start in range length of S. So we check all indices in S. And we want to do this quite quickly. So we need a quick way of figuring out. I wonder if this thing is slow. This find next not used. So I wonder if this find next not used is slow. It might be, because if I look at the example that this guy failed on, this like giant A, perm or used is going to get larger and larger. Okay? And then this find next not used is going to get a little bit slow. It is going to get a little bit slow. So let's go with, let's get rid of the find next not used. Let's instead go with this strategy. This strategy where we do word times. Okay, cool. So we have to build a word times. Let's start with this first. I'm pretty sure this will save us a little bit of time. But I think it will still fail. Yeah. Yeah. So one thing that I sort of was subconsciously programming for was that I kept not using this stipulation they had, which is they're all of the same length. This actually makes things a little bit easier. You know, like this foobar example is out. And also when I want to check word at index, I don't have to search anything. I just take as blah this. Yeah. This makes it a little bit easier. Okay. Now let's do word times. Actually, let's not do it. Let's run this first and see what happens. I think this should work, but it's slow. Name lookup is not defined. Where do I have lookup? Yeah. Wrong answer. Let's try this. Let's try this. Okay. So you can see here that I'm doing a pretty big facelift of everything I'm doing, right? I'm getting rid of a whole bunch of stuff. But the nice thing is, apparently, most of the code is reusable. I think the top processes are also reusable, which, in my opinion, is kind of the more important thing. Okay. So self is not defined. Ah, damn it. Okay. Let's see what happens when we do this. Good, not in list. That's fine. Oh, I need to change this to the try, whatever. Try equals accept. Visualize execution. Okay. Cool. Let's see what we got. Word and index is good. Find next not used. Oh, that's not good. Words is this thing over here. Is good not in this list? How is good not in list? What's previous index is 4. Okay, you know what? I'm not going to debug this because I'm going to change the way we do things anyway. Yeah, this good not in list, this thing is going to run super slow. Yeah, it's going to run super slow. This thing runs super... Oh, not this thing. Find next not used runs super slow. When words is just a giant array where every word is the same word. That's going to be super slow. Yeah, like this, that AAA whatever thing. That's kind of annoying. Okay, so word times. We're going to create a mapping. So for word in words, can I do this? I wonder if I can do this. Can I do Python not in? Alright. Oh, I can do not in. Oh, learn something new today. Okay, so if not in, want in word times, then word times word equals to 0. Else, word times. Oh, not else. Word times word plus equals to 1. Okay. So this will tell me how many times the word occurs in word times. Okay, cool. We're gonna have small data structures now. Word times is gonna be a dictionary, is gonna be small. Used just now, use was gonna grow super huge. For that particular example with a bunch of A's, words is gonna grow super huge. And we don't want that. So we're gonna do it this way. So this is out. So used is now can I make a deep copy? Can I make a deep copy of a dictionary? Import copy dot deep copy. Yeah, let's do a deep copy. Oh, dic1.copy. Okay, so I don't need anything fancy to do here. It's not actually a deep copy. I don't need a deep copy. I need a shallow copy rather than a reference. So I need to copy the first level. Word times dot copy. Okay. I'm going to do a demonstration later. What happens when I set this word times? Not true. Okay. Word at index equals to this. Okay. And then now, if word at index not in used, then valid equals to false, break. So let's talk about what I'm doing here. What I want to do here is the following. Used is this thing right here. So word times is here. I want used to start with word times. So instead of counting up, I'm counting down. When idx equals to 4, so when idx is 0, I see the word good, right? Right here. So I'm going to go to word. The word word, I'm going to set it to 0 and decrease by 1. Right? So when idx equals to 4, word and index is word. When idx, and so I decrease good by 1. So that's my strategy. That's how I'm going to do things. When this is 8, okay, word at index is going to be good again. And then now this thing goes to 0. Yeah, so I'm going to keep a ticker of what's going on here. Okay, word index not used. Break. Otherwise, used. Use or used word at index equals to 0, right? So copy this to the top. So you see I'm decrementing. So what when IDX equals to 12, this is where it gets interesting. So 0, 4, 8, 12. Is this good? So IDX is good again. And then now we see that good is 0. And we say, hey, you're trying to use 3 goods. You only have 2 goods here. Here and here, you're 2 goods. You're trying to use a 3rd good. So this will fail, right? So this is what's happening. IDX or break use. Otherwise, IDX word at index minus equals 1. So it decreased by 1. Yeah, I think this should work. And we get rid of all the finding bullshit stuff. All this finding nonsense is gone, which is great. I never liked it. Let's run it, see if it works. Wrong answer, nope, not good. Okay, let's see where we went wrong. It's 11. Normally I just stream for 1 hour, but I think today, because we're so close to getting the results, let's just finish this up. Okay, visualize execution. Okay, we're gonna start from here. Okay. So here, let's look at what we have so far. Word times. Where's word times? Word times, good. Word is good. I hate this. Word is 1, good is 2, and best is 1. Word, 1 occurrence, good, 2 occurrences, and best, 1 occurrence. So this makes sense. So good word times is correct. So used you notice that used has its own copy of the same identical dictionary as word times. This arrow doesn't point back to this same data structure here, right? Remember this. Actually, I'm gonna just duplicate this. If I don't do word copy, if I just say used equals to word times, what happens? Visualize execution. We'll come back here. We go next. Okay. Look very carefully what the difference is. Look at what the difference is. You see this? Word times points to a dictionary. Use points to the same dictionary. That's what happens when you say use equals word times. Because we're copying. So word times is actually not this dictionary here. It's this arrow here. We're saying copy that arrow. But when we do word times dot copy, we're saying make a duplicate of the thing the arrow is pointing to. So now we have these 2 arrows point to different dictionaries. Do you see what the difference is? And the reason why that is important is because we're using used as a counter. We're decreasing these numbers in used. And we don't want to cause any changes to word times. We want word times to stay the same. We're decreasing the numbers in used without changing what word times is. Okay, that's just a little digression. Okay, so where were we? Okay, so let's see what happens. Word and index. Word and index is word. That's correct. Right? IDX is 0. Word is word. So IDX is 8. You can see what times is going down. IDX is 8. Zero, 4, 8. So now IDX is good. Word and index is good. Just like we predicted. We can see these counters going down. Okay, we lost the word, we lost a good. So we use another good. Okay, see now good is 0. Okay, and then now IDX is 12. Word index is good. We have good here, but unfortunately we ran out of copies. We only have 2 goods. But this word wants us to use 3 goods. So we ran out of copies. Valid equals to false, break. Perfect. This is what we were expecting. Now let's go. And now IDX, now start is 1. Start is 1. Word at index is org. This doesn't even exist. So valid equals false. Perfect. This works well. Okay. So it's supposed to return. Okay, what was the answer supposed to be? This works well. I wonder what's going on. Okay. Actually, let's debug this first to make sure this works well. So that it's supposed to. So when start equals to 8, right? Good, best word is actually a valid thing. It's actually a valid index. So let's keep going. Let's see what start is. Start is 2, 3, 4, 5, 6, 7, 8. Okay. Now, start is 8, valid is true. Used. We set used. Okay, great. Okay, now word at index should be good. So, when start is 8, we should get good, best word, right? Good, best word. And good, best word should be a valid permutated string. So let's see what happens. Okay. So we use a good. That's great. Word at index, another good. We use another good. Okay, that's great. And now word at index is 16. 1, 2, 3, 4. So now word at index is best. Word at index is best. Yep. So we use a best. See, this best should go down to 0. We use a best. So good, best. We have 2 goods. We use 2 goods already. We use the best. And now word at index word. And we should use word. Okay, so now valid is still true. Let's make sure this exits. Start is 8. IDX is 20. Length is 4. So start plus n times length. Start is 8. N times length. N is 4. 4 times 4 is 16. Yeah, so it should be right. Append start. Yeah. Result is 8. Yeah, this is correct. Okay. So what's wrong with this then? Why is it complaining that this is wrong? Case 1 is wrong. Case 2 and 3 are correct. This is very interesting. Case 1 is supposed to be the easiest case. Let's see what happens. Ba fu the fu ba man. Okay, let's edit the code. Try again. Ba fu the fu ba man. Okay, and words is fu and ba. So if there's one thing to take away from all of this, I'm gonna hop on this again and again, is that don't be afraid to just try things and change tack when things don't go the way you expect them to. Right? Don't be afraid to just like mess around, see what happens, change things up a little bit. It's fine. Okay. Let's go to last. Answer is empty list. This is not what we want, right? We think that ba fu and fu ba are both valid answers. So let's see what happens. Let's see what happened. So this is the most interesting part. Let's come to here. Let's go to here next. Okay. So start equals to 0. Okay. So start equals 0 should be an answer, right? Because bar foo should work. So let's see what went wrong here. Start equals to 0. Okay. Next. Word at index is. Why is word at index bar? It should be BAR. I see. So n is the number of words. This should not be n, this should be length. This should not be length, this should be n. Sorry, this should not be length, this should be length. Length of the word. Okay? So for the other case, that worked because we happen to have 4 words of length 4. But this case is different. Okay, alright. I think this should work. Nope, doesn't work. Oh, yes, it works. Let's see what happens when I submit this. This should be faster than everything else we've done before. Okay, perfect. So it is faster. It's not the fastest. You know, I definitely blame my machine for this. But it is faster than everything else we've done before. And also, we can now get rid of this. Okay. So you see how we went quite a circuitous route. We started going on a very different journey at the beginning, right? We started, in fact, we didn't even start with lookup. We started with this thing called occurrence. And then, if you guys remember from last time, we started with occurrence, which is like this. And then we're like, oh, this occurrence doesn't really work very well. Maybe let's change it to lookup. And then later on, we realized that actually lookup is unnecessary. Lookup is not useful at all. We skipped the whole lookup thing, and we just did start from range S. We just go index by index. This means that we save a bit of time populating lookup. We don't have to search for these words inside the word. We don't have to search for these words inside S. We don't have to search for all occurrences of word inside S, which is fine when words and S look like this. It's not fine when S is like A, and then word is like A, comma, A, all the way to infinity. All right? So this is an example where things are not fine. Okay. No questions here. Yeah, and then we eventually also drifted towards saying, hey, you know, we did search thing. We did a whole search thing. Okay, and the search turns out it's very slow for large cases. So we instead switch to a dictionary case. We switch to this case. I would love to talk about how I came up with this. You know, I didn't really explain how I came up with this idea of using a dictionary. I just said, well, there are two ways to do it. One is this way, the slower way, and one is the faster way. I want to say part of it comes down to experience, but maybe I'll do a video on a different day explaining how to get to these kind of strategies quickly. What's the way you can train your brain to think, to explore the sort of corpus of different strategies. Okay, so I think that should be, yeah, that should be it. Before we go, let's find another problem to work on. I am going to pick an easier problem this time. I'm still going to look at this premium thing. It looks like the premium gives you the debugger. Wow, $129, huh? Yeah, built yearly. Built monthly, $35. Oh, God. I'll think about it. I will have to think about it. I wonder if there's like a trial period to see how it works first. But I'll think about it. As you guys know, this YouTube channel is brand new. We are not making bank right now, so we're gonna have to make do with what we have. Let's look at what other top problems we can. We're gonna pick an easy one. You know what? Let's just do a medium one. I want something less abstract this time. Spiral matrix. Sound kind of fun. Let's see what it looks like. All elements of the matrix in a spiral order. Interesting. Very interesting. Let's try this. Alright, let's try this. Sounds kind of fun. Okay, so next time round we'll be working on number 54, spiral matrix. I'm gonna post the link in the schedule so that you guys can see it next time. And that will be it for today. Thank you very much and see you next time. Bye.